Hello and welcome to the lecture Multimodal Deep Models. In this lecture, we are going to discuss cross-modal visual semantic embeddings, image to text captioning, then conditional image synthesis, generative adversarial text to image synthesis, then what do we mean by multimodal features and fusions, and we conclude this lecture by multimodal contrastive models. To understand the different multimodal deep learning model, first we start with cross-modal visual semantic embeddings. First we understand what we mean by that. So the cross-modal visual semantic embeddings refers to a framework in which data from different modalities, primarily images and natural languages, are mapped into a shared semantic vector space, such that semantically related inputs lie closer together regardless of their form. Now, what do you understand from this statement? That before that we understand the individual embeddings from a single modality. That if there is an image, that is the image embedding, that is in visual space or visual speech space. If there is a text model or text input, we can get a text embedding. This is another text space. Now, what here we are doing, there is a multimodal data, or here it is a bimodal, that one from image and natural language. And what we are here interested, we are not a single space, that it's kind of a, you can say, multimodal space. So it's a shared semantic vector space. Okay. So data from different modalities are mapped in this shared semantic vector space. Okay. Such that semantically related inputs, that maybe there is a cat image and it is written this is a cat. These two modalities, maybe two different modalities, but it somewhat indicating some cat images or some cat information. So these two inputs, although it is from the two different modalities, it is semantically closer, so semantically related, and that's why these semantically related inputs are lie closer, so it will cluster in a very neighboring position regardless of their form, and that is very important to understand, and that is called visual semantic embeddings. Okay, in this approach, visual feature extracted from images, that visual feature, it is for CNN or transformer encoders, whatever, and some linguistic represent derived from words or sentence are jointly learned, and that is very important, they are jointly learned using objectives that encourage alignment between corresponding image text pairs while separating the mismatched ones. Now, in this joint space or shared semantic vector space, those projections from different modalities, just what I said, that this is a cat image and the sentence this is a cat, these two, even if they are from different form or different modalities, they are lie closer. But if there is an image of kite and it is that this is dinosaur, these two things is not going to be lie very closely. So this is very important to understand that this jointly learned such that the objective, what is the objective? That encourage alignment between corresponding image text pair while separating the mismatched ones. So those are mismatched, that is. So the early work such that this Richardson demonstrated how this shared embedding enables cross-modal transfer, allowing models to generalize concept learned in one modality like textual description to the another like images, thereby supporting tasks such as image retrieval, annotation and zero-shot recognition. So this is basically the visual semantic embeddings. Now we try to understand this cross-modal visual semantic mappings or embeddings by a work by Richard Soher in 2013. The name is basically cross-modal transfer. So this work proposes a method to transfer knowledge between modalities, text modalities and image modalities. This is a bimodal model or the scenario where we transfer knowledge between these two modalities, text to image or image to text, by learning a joint embedding space. Now here you can see this is the manifold of known classes, and there is some images and there is some text data. Okay. Now the question is that this training images is being projected on this manifold or this space of known classes. Okay. So these are the images of different objects. Say it's a car images, this is a dog image, a horse, and something like that. So that what is our basic, this manifold is not a simple image manifold or image space or image feature space. It is basically a joint embedding space. Okay. So images and words and sentences are mapped into a same vector space. So now the question is that this semantic similarity is preserved across modality. Now what do we mean by semantic similarity? Semantic similarity means that let's say there is a image of horse and some text related to horse. If these are two different modality, one is from image modality, one is from text modality, but semantically they are close because they are somewhat regarding this horse. So in that way that is semantically similar. So semantic similarity is preserved across modalities, and this allows the model to generalize concept learned in one modality to another. So that is the basic concept. Before this paper, at the time when this paper is proposed in 2013, most models treated images and text separately. So it's a kind of unimodal. This work introduced a shared semantic embedding, a way to align visual features with linguistic meaning. So that is very important to understand. What the alignment is done? It is a visual feature that has some linguistic meaning. So they basically introduced a shared space or shared vector space that accommodate not only the image feature but some linguistic feature or text features. The image representation, how the image is being represented in this space, uses the feature from the pre-trained CNN. Each image is converted into a vector, and that vector is basically projected in this space. Okay. Now what is the text representation? Use the word embeddings, combines them with a neural network. Yes, that they use the recursive neural tensor network in some areas. So whatever the neural network, they have used it. And that two embeddings, one is image embedding and is word embedding. And this joint embedding space, both image and text vector are projected into the same space. That is the main novelty. That was not done before. So what is our training objective? That match correct image text pair. So correct image text pair means there is an image of horse and some text regarding the horse, then it should be closed. The projection or these points, clouds are closed, or this feature, when they are projected, this image feature and the text feature in this kind of subspace manifold, or you can say that shared semantic space, these two are to be closed. Whereas if there is a image of horse but text regarding car, that should be further apart. So a bit contrastive. Ideally it is contrastive, not. So this is the basic idea of the cross-modal visual semantic embedding by this paper of this course. Okay. Our next multimodal deep learning model is basically on the idea of image to text, that is image captioning kind of thing. Given an image, can we generate some text on it? So here there is a very important paper, kind of a very landmark approach, that show, attend and tell. This model is proposed by Kelvin Zhu et al. In 2016. The model by Zhu et al. In 2016 is as a landmark approach, is a very important model in image captioning that introduced the use of attention mechanism. That the attention is one of the key features of transformer architecture or transformer based models to generate more accurate and descriptive captions. So how it different than the contemporary models? So unlike earlier models or existing models that encoded an entire image into a single fixed vector, this method allows the model to dynamically focus on different regions of an image, and thus the attention. Because attention is a kind of mechanism which selectively put some sort of priority on the part of the input modality. Let us say if it is a sentence, they will put some words, not all words. But if it is a images, that they put emphasis on some patches or some objects rather than all the full images. So that's why it is saying, unlike earlier models, these models encoded entire image into a single fixed vector, which is by the basically the existing model too. This method allows the model dynamically focus on different regions of the image and while generating each word in the caption. So this architecture combines a convolution neural network CNN for extracting spatial image features. So that you can see that is spatial image features, convolution feature extraction is being done with a recurrent neural network within some sort of RNN, typically an LSTM that produces the caption word by word. So this is by this, and then LSTM that will generate this. Okay. At each step, an attention module assigns weights to different parts of the image, effectively deciding where to look before predicting the next word, and that is very interesting. So why attention here? What they are basically do, attention module is going to say which part of the image is important, where we put more emphasis, where to look the image before, and based on this you predict the next word, and that is very interesting, and that is one of the major contributions of this one. This results in captions that better reflect the fine-grained result and object relationship within the image. So, the model also introduced both soft deterministic and hard stochastic attribution variants, further advancing research in interpretable and context-aware visual language systems. So, this is a very important work here, where this image to text or image caption is. Okay. Now, next idea, the conditional image synthesis or conditional image generation, that is text to image, that give us some prompt. Can we, based on the prompts, we can generate the image. So, conditional image synthesis refers to the task of generating images based on a given input condition. Most commonly text description, class labels, or other modalities. So, I repeat, conditional image synthesis refers to the task of generating images based on a given input condition. And this, what is the input condition? That most commonly text descriptions, okay, class labels, or other modalities. So, if you say the red bird with black wings sitting on a branch. So, based on this description, can we generate the image? This is a very hypothetical taken from internet, but the thing is that, can we do this? The goal or objective of this work is this. So, in this text to image setting, the model learns to translate a natural language prompt. We said this is the prompt. This is a red bird with black wings sitting on a branch, into a realistic image that matches the semantic content of the description. Now, what is important to understand here, that given a description in a particular modality like text here, that we try to understand what are the internal meaning of that, and being understanding or having understanding of that meaning, we try to generate the image. Okay, so it's a kind of conditional generation or conditional GAN kind of thing. I am not saying that this is on the GAN, but the idea is kind of thing. The condition is based on one modality and output is a different modality. Okay. Now, this is typically achieved deep generative models. What we just said, this GAN, the generative adversarial networks or diffusion models, where the conditioning signal, here the text embedding, guides the image generation process. So, in conditional GAN, what we have seen before, that some condition is being given, and that condition given by virtue of this text embedding, by some text or prompt. So, early work such as conditional GANs and later architectures like stack GAN demonstrated how textual embedding can be used to progressively refine images from coarse to detailed representation. For example, generative adversarial text to image synthesis is very this. So, more recent systems, including the models like DALL-E, extend this idea at scale by leveraging the large multimodal dataset and powerful transformers of diffusion-based pipeline, enabling the synthesis of highly diverse and photorealistic images aligned with these complex textual prompts. Okay. So, this is interesting. This paradigm is key component of the modern multimodal AI, bridging the language understanding with the visual creativity. So, this is basically the text to image concept. So, this is our next concept is generative adversarial text to image synthesis, that is Scott-Reed et al. In 2016. This is also another pioneering work that introduced one of the first successful frameworks for generating images directly from natural language description, like generative adversarial network. Okay, the model conditions the image generation process on text embedding derived from the captions, typically using a recurrent neural network to encode the semantic meaning of the text. So, they put a recurrent neural network here to understand the semantic meaning of the text. These embeddings are then fed into a generator network. So, this kind of a generator network that produce the images where a discriminator network learns to distinguish not only between real and fake images, but also the image matches the given text description. So there is a two type of loss. One is definitely the adversarial loss, that it looks quite natural, and how it is aligned with the text description. So these two things will be taken care of. Okay. So this joint conditioning encourages the system to generate visually plausible images that semantically aligned with the input text. Okay. And this work impressive result on datasets like birds and flowers, showing the ability to generate the fine-grained details from textual cues. And this is a very important work because this work laid the foundation for later advances in conditional image synthesis and multimodal genetic modeling, and that is very, very important. Okay. Now we are going to discuss what is the basic challenge we are going to face when this kind of multimodal deep models are being implemented or designed. So one of the major things that when we are dealing with multimodal data, that one modality can dominate other modalities. That, let's say for our image and text modality, sometimes it is seen some text is basically more prevalent over images. Another case, it may be the possibility that if they are not very well synchronized, the additional modalities can add noise. So additional modalities can be treated as a noise, and sometimes the full coverage over modality is not guaranteed in this model. So these are the challenge what we have to keep in our mind when designing our multimodal deep learning models. Now important thing is that what are the multimodal features? Just if we just text feature consider that batch size into in multiply into sequence length into the hidden size. So these are the basic feature dimension or feature size. Now when come the image, so we can do this kind of this image batch. It's more simpler to understand, or sometimes object kind of thing. So the object detectors here like this, or this kind of the feature maps kind of convolutes on feature maps. Vision transformer we can also use. So vision transformer, this patch is used there. So these are the multimodal features similar for image and text. Now there is some other things, the region proposals, region based features. So they are some of the very well known algorithms. So some of already we covered, that RCNN, first RCNN that we have covered in our earlier lectures, and some YOLO that also seem kind of similar, and mask RCNN that are. So these are the kind of region proposal. That's the kind of object detection and the bounding box based object detection. So these are the region features and used as a image modality or the submodules of this image modality. Now important is multimodal fusion. So if there is some different kind of you can say way to fuse two modality. If it is similar, just we take the inner product U and V is coming from U is the one modality, say text, and V is some sort of vision or image model. So inner product. If we just concat, just add it, so it's a linear or sum. It's a concat sum max of these two, this or sum weighted something. Okay, so some multiplicative things. So we can do some multiplication, element wise multiplication, or some use some gate over it, and LSTM style this kind of tonnage of this. So getting mechanism are used for this multiplication. Next comes the attention. Attention means know that we have to put some emphasis on some portion or modulation kind of. some interpolation, the bilinear interpolation, the bilinear things is not interpolation, it's a bilinear approach, that you bilinear graded, low rank bilinear, compact bilinear, and so on. So these are the way the features can be fused. But the problem, when to fuse, at what position to fuse, and based on this, there is three major things in multimodal fusion, that is early fusion, middle fusion, late fusion. Here we try to understand here these figures. Now in this early fusion, this feature level fusion, so at the feature level if you fuse it, so you can say these are the image embedding and text embedding, and fuse these two embeddings, and after fuse, just for example, is we concat two features, and then it's put to the some deep neural network. It may be CNN, it may be RNN using transformer, whatever that you can put. So that's the early fusion, that image and text embeddings done and it fuse. So it's a feature level fusion. Now it's a mid level fusion. Mid level fusion means sometimes we use some sort of deep neural network, it may be a CNN, it may be an RNN, and to get some sort of representation, feature representation from this particular neural networks, which are basically more suitable for this kind of modalities. So in middle fusion, early each modality is first processed independently, and their intermediate representation are combined at some point of inside the model. So this exactly. So after some processing we fuse. And the third option is late fusion. We fuse the decision. We physically put all this in separately, and what we get the decision here, the inference, and we fuse it. So in late fusion, each modality is processed separately all the way to the output stage, and then final predictions are combined. So these are the very important, this multimodal fusion. Okay. Our final and most important model is multimodal contrastive models. These multimodal contrastive models are a class of learning frameworks that align data from different modalities, such as image and text, by training them in a shared embedding space using contrastive objectives. So that we know that what is the contrastive thing, that these pairs of data which are close, they are put in a close vicinity, and those are the different, they put it in distance. The central idea is to learn representation where matching pairs, an image and its correct caption, are pulled closer together, and while non-matching pairs are pushed further apart. That is the basic idea of contrastive. Typically, these models use a dual encoder architecture with separate network for each modality. This is for a vision encoder or a language encoder, whose outputs are compared with similarity measure like cosine similarity. Okay. During training, a contrastive loss such as influency is applied over batches containing many positive and negative pairs, enabling the model to learn the fine-grained semantic alignment. So that is very important to understand, that the semantic alignment is very important here. Basically, we are taking the information, or basically we are projecting a particular space from different modalities. Let's say from, if we are from image, there is an image encoder, we get some feature space or features, and that is projected on a shared space or shared feature space, both from image and the text. So typically these models, so that's why typically this model uses a dual encoder architecture with separate network for each modality, a vision encoder for language encoder and a language encoder. So outputs are compared similarity measure like a quotient similarity, and this is placed in shared space. Okay. And how it is been placed in this shared space and the shared embedding space based on their semantic alignment. Those are close, they are put together. They are not closed, they are non-matching pair, they are pushed apart. So that is the basic idea, multimodal contrastive models. So a prominent example is CLIP, that will come later slide, which demonstrated that the large-scale contrastive pre-training on image text pair can produce highly generalizable representation. That we will see. These models supports powerful capabilities such as zero-shot classification, cross-modal retrieval, and multimodal search, as they can associate unseen concepts across modalities using natural language supervision. So the multimodal contrastive learning has become a foundational paradigm in modern AI, influencing a wide range of systems that integrate vision, language, and beyond. So that is very important thing, that this particular, what is the CLIP, is a very popular model under this multimodal contrastive models. So this model supports powerful capability of zero-shot classification. Now what do we mean by zero-shot? We already know that what is meant by zero-shot. That means that this, without having seen a single instance of a class, that can understand or they can classify that particular image at time of testing, that this is this particular class. Class we do know, but they not single instance of the training time. Cross-modal retrieval, multimodal search. Cross-modal retrieval means given an image, we can get some text, or vice versa. So given text, we can retrieve some image. Multimodal search, as they can associate unseen concept across modalities using the natural language. Okay, so let's see what is CLIP is. What is one of the most popular contrastive model? CLIP stands for Contrastive Language Image Pre-training. This model is a multimodal framework that learns a shared representation of images and text by training on large-scale image caption pairs. Now, how it works? It employs a dual encoder architecture. One encoder for image, such as CNN or Witcher transform, and another encoder for text, for example, transform, that independently map the inputs into a common embedding space. So that is very important. Next thing, using a contrastive learning objective. And what is contrastive learning? The model brings matching image text pairs closer while pushing non-matching pairs apart, and that is the contrastive learning, enabling it to capture high-level semantic relationship across modalities. So in CLIP, there is two major things. One is contrastive learning, another is multimodal modeling by project this image and this text modeling in a common embedding space. And when they project these are in common embedding space, there is a pair, image text pair. If an image is about a horse and a text about a horse, these pair are closely placed. Whereas if there is an image of, let's say, horse and text of car, these are these two further apart. So this is a contrastive learning idea. So this contrastive learning objective in this common embedding space, this multimodal data are being placed. Now this is the CLIP model. So this is the image. This is the image encoder. They put these image features, or if it is CNN features, or is a transformer. And this is the text. This is a transformer encoder, and it is a, and these two feature we have. If you fuse, we get this. This is the using the contrastive loss. Next, another most important capabilities of CLIP is zero-shot learning. What do you mean by zero-shot learning? That we learn previously that without having a single image at the training time, if we know the class, we can use that some semantics relations, and with known class we can classify a class or a test image to a particular class. That is basically zero shot. Now here this can be done. It can perform tasks like image classification without task specific training. That's what we say. There is no training image at the training time. By comparing the image to textual prompts, that is one of the major advantages of it. And this approach eliminates the needs of level dataset for every task and made Eclipse a foundational model for applications such as image retrieval, multimodal search, right, generative model. So Eclipse is a very important model. And here you can see that the use of zero shot prediction image encoder, and this using prompt we can say that this basically image of this a photograph of a particular object. So that is so in summary, in this lecture we understand different aspects of multimodal modeling as cross-modal visual semantic embeddings, image to text that image captioning, conditional image synthesis, generative adversarial text to image synthesis. Then we understand what are the multimodal features and what are the fusions is, and we conclude by multimodal contrasting. In this next lecture we discuss visual learning. Thank you very much.